a two-step process when you're going to test a function to determine where it's increasing or decreasing. It's a two-step function. If you're going to need to find critical numbers, and then you're going to need to test values on either side of the critical number to see if the function is increasing on one side of the critical number and whether or not it's decreasing on the other side of the critical number. So the first skill we need to acquire is actually finding these critical numbers. So let's go ahead and do that. So if you've got your notes, we've got the critical number for the function g of x, which is equal to x plus 2 squared. So it asks us to find the critical numbers of this function. Okay. So in order to do that, first of all, we have to find the first derivative. Okay, because the critical number, it says, is a function defined at c, and it's a critical number if the derivative is 0 or the derivative is undefined. So the first thing we need to do is find the derivative, because then we can tell where it's 0 or where it's undefined. Okay, so I'm going to use the chain rule here, the general power rule. So the 2 comes down, leave the inside alone because I haven't finished with the outside yet. So the first power times the derivative of the inside, which is 1. So this is 2 times x plus 2. Now the next thing is critical numbers are places where g prime of x is 0 and g prime of x is undefined. So g prime of x is 0. That means when 2 times x plus 2 is 0. Well, 2 can't be equal to 0, right? We have two numbers being multiplied, and their product is 0. That means one of those numbers has to be 0. Well, 2 obviously isn't 0, so that means x plus 2 has to be 0. So that means x has to be negative 2. And is our function g defined at negative 2? Sure. Negative 2 minus 2 is 0. 0 squared is 0. That works. So here's one critical number. We have to determine where is g prime is undefined. Well, let's take a look at 2 times x plus 2. Is that undefined anywhere? Are there any places where we would either be dividing by 0 or we might have the an even root of a negative number? And the answer is no. This is a polynomial. This is, in fact, a line. So it has no holes, no gaps, no asymptotes. This is defined everywhere. Okay, so we have just this one critical number. Therefore, x equals negative 2, the only critical number for g. Okay. And that's where we have a horizontal tangent. In fact, we can tell that because the derivative is 0. Okay, so we have one critical number. All right. So that's pretty straightforward. You find the derivative, determine where it's 0, determine where it's undefined, and then you go from there. Okay? Just always make sure you check, is the original function defined at that number that you get out of setting the derivative equal to 0 or finding where the derivative is undefined. Okay? You might say, well, if the derivative is undefined, wouldn't the original function be undefined there? And the answer is no, not necessarily. You will find examples, for example, the cube root function is defined everywhere, but its first derivative is undefined at 0. In fact, we have a vertical tangent line at x equals 0 there. So there's a case where a derivative is undefined at a particular point, but the original function was defined there. So you do have to be careful of those. Okay. So our next item of business is to apply the test for increasing or decreasing. So there are a couple of steps that you'll need. The first one is to find all points of discontinuity of f, find f prime, find all critical numbers of f. We'll use that to create a chart, and then we'll use that chart to test the sign of the derivative to determine where our function is increasing or decreasing. So let's try this out to see where this particular function, y equals negative x squared plus 2x. We're going to determine where that's increasing and where that is decreasing. So first step, as we mentioned, was determine all points of discontinuity. This one has no discontinuities. It's a polynomial, and we had a theorem that said polynomials are continuous everywhere. Right? This is a parabola, in fact. Its graph is a parabola. Okay, the second step says to do what? We need to find the derivative. Okay. So y prime is negative 2x plus 2. Step 3 is use that to find critical numbers. Okay, so we want to find out where y prime is 0, where y prime is undefined. So we set negative 2x plus 2 equal to 0. So that would be, let's see, I'm going to add 2x to both sides to get 2 equals 2x. Divide by 2, we get x is equal to 1. Okay. Y prime, is it undefined anywhere? Well, again, we've got a polynomial. Right? In fact, it's a first-degree polynomial, so the graph is a line, and this is defined everywhere. Okay. So we check x equals 1. Is that our critical number? Just double-check, make sure. Is it a point? Is it a value that I can plug into the original function? Yes, because we have no discontinuities by step number 1. So x equals 1 is our only critical number. Okay. Now what I'm going to do is I'm going to erase this because I need to make a chart. So what I'm going to do is, right, I'm going to have us recall what our original function was. I prime equals negative 2x plus 2, and we have a critical number of x equals 1. Okay, so I'm going to use that to draw a graph, or draw a chart, in fact. So the way that this chart is drawn is you're going to have function in one column, and then we're going to have intervals. So we're going to have a function y and our function y prime. And then we're going to have our intervals here, so negative 1 to 1. And our intervals are created by using our critical number. So our critical number is 1, right? So we're going to break the real number line at 1. So I have the interval to the left of 1, which is negative infinity to 1, and then from 1 to infinity. And in fact, I don't, well, anyway, I don't need this guy here. I need test value and sign. Okay, so this is to indicate I'm using y prime, and I'm going to do pick a test value, and then I'm going to determine the sign of y prime. Okay. So in this case, I wanted to pick something in the interval from negative infinity to 1. Now, why do I just need to pick one value? Well, let's see. We analyze the derivative. Remember, keep that original drawing I had. Keep this guy in mind. It's not the graph of this function, but keep that in mind. Remember, our critical numbers were places we had tops of hills, bottoms of valleys, right? So those are the only places where the derivative is 0. Okay, so we have only one place where our derivative is 0. In fact, it's an upside down parabola. So we have just this one place where the derivative is 0. Now, since that's the only place that derivative is 0, anything else, the derivative would have to be either positive or negative, correct? And it's also to the left of that critical number where the derivative is 0. It's not going to change sign because that would mean we'd have to have something like this first graph above here that I've drawn. Right? In order for it to change sign, it would have to go from positive to negative, and in order to do that, you have to go through 0. If you think of the real number line, in order for me to get from the negative side to the positive side, I have to go through 0. So that's why I only need to pick one test value in each interval. Okay, so let me pick something easy, something in the interval from negative infinity to 1. Well, 0 is a nice easy value, right? Okay, and then from 1 to infinity, 2 is a nice easy value to use. And what I'm going to do is I'm going to figure out the sign of y prime, okay, determine is it positive or negative at that value. So when I plug in 0, I get positive 2. So my sign is positive. If I plug in positive 2, I get negative 2 times 2 plus 2, which is negative 4 plus 2 is negative 2, is negative. All right, so remember that we've got, in this case, positive slopes of tangent lines to the left, and I've got negative slopes of tangent lines to the left. So that tells me two things. This is increasing to the left of 1, and it is decreasing to the right of 1. I'm getting that from the sign of the derivative. So I would say, my final answer would be, this is increasing on negative infinity to 1 and decreasing on 1 positive infinity. And you can always graph these to double check to get a visual confirmation that in fact you're increasing or decreasing. Okay?